Okay, let's see if I got this. Okay, well, see, I'm going to be talking about the cyclical nature of exploration of the moon, where we've been, where we're going, and by that I mean we, all people on planet Earth. Okay, oh, this is my last slide. Could we go to my first slide? Okay, thank you. For exploration of the solar system, there are various different elements, remote analyses, in situ, and sample analyses. And this is true for virtually most of the places we're exploring in the solar system. And this is a cyclical thing. You don't do one and then you're done. It's a cyclical effort in order to understand how things work in our solar system. For the moon, 50 years ago, we completed the first cycle. It was wonderful. We had remote measurements, in situ, and sample analyses. And these are what we've been celebrating for the last week and up to today and tomorrow. Now, jumping ahead to the present, of course, we've been having additional cycles. With additional countries involved in this. Of course, it's not complete. We recognize from this that the information we've gained is a small part of a vast unknown. However many cycles we've been through with different parts of this exploration, the more we learn, the more we realize we have a lot yet to understand. And that's where we are at the present. One of the important things that has come out of the last 50 years is understanding the relationship between the two parts of the Earth-Moon system. They're extremely tightly coupled from the beginning up to the present. And this has been a really important and ongoing area of research that's really a foundation of the importance of the moon in the Earth-Moon system and our understanding of our place in the solar system. The moon, in this context, has often been called the eighth continent. And that especially is pertinent in terms of where we're going in the future. Here's a vast area that has components on it that we understand to a first order, but we want to understand in more detail and utilize in the next 50 or 100 years. So, where we're going in the near future? Well, I think many of you, well, the reason we're here is probably to discuss that, and to be discussing that for the next 50 years. One of the important things in the near future that's recognized and has been clearly evident in the last couple of decades is that this is a multinational activity. Each of these cycles that we're still involved in involves not just the two initial spacefaring nations, but virtually all the spacefaring nations across the globe. And this will continue expanding to the commercial area as well. This makes it a very strong and integrated activity as we move forward. Of course, the remote analyses, you don't do it once. There's every time you do a exploration with whichever instruments you're working with, you learn an incredible amount, but you also learn what the next step is, the major events that we don't understand, that the technology of the instrumentation that is being developed will allow us to address. Clearly, in the near future, we will have new landers on the surface. We expect a large number of these with a diversity of both countries and commercial involvement. And in this round, and probably for the next several generations, there will be an intimate human-robotic interaction. The technology demands that and encourages it and will allow the capabilities in the future that are going to be establishing this as an important part of the program. And of course, sample analyses. This is a key central part of our analyses, the kind of detail that can be understood from samples, the diversity of samples, and specifically why samples are so important is that we have large instruments that continue to evolve in capabilities, the things instrumentation can do in Earth-based laboratories in the present day is astounding. And for those of you who are not involved in this field, I encourage you to be investigating this because it is another whole area down to the atom level of sample analyses. Okay, what I'd like to do is briefly walk through, because half of you weren't there when we landed on the moon 50 years ago, some of the highlights of the series of sample return missions to the moon. The first, of course, the one we're celebrating currently is Apollo 11. It brought the first samples back. We found they were high titanium basalts, very, very ancient. That was a major breakthrough. It can't be underlined more strongly. We learned from that very quickly that there's these basaltic maria and the feldspathic highlands. That little pink circle is the entire area that all these sample return missions sampled. So you notice, first of all, that the total is from a small area on the moon. Okay, let's move forward. Apollo 12 and Luna 16 both sampled additional basaltic terrain, completely different from the ones that were sampled by Apollo 11. This showed the diversity of samples in basaltic terrains and set the baseline for understanding basaltic volcanism on the moon. When we got to Apollo 14, we began to recognize that there's this highly unusual potassium rare earth element abundance in the samples that was not understood or not even predicted, and today still puzzles us what this implication is for the evolution of this planetary body. Apollo 15, Lunar 20, and 16 I looped together because this expanded our understanding greatly in terms of the feldspathic component of the lunar crust. The feldspathic breccias, it expanded additional basaltic terrain, and especially for Apollo 16, although that landed in an area which turned out to be essentially feldspathic terrain, it was predicted to be volcanic. You have to go back into literature to realize that the morphology of the area strongly suggested this was going to be volcanic. We got there, it was not. And that told us we had to understand the character and the evolution of surfaces in a much stronger detail. Of course, Apollo 17, we could not live without Apollo 17. Apollo 17 not only returned us samples that were comparable, well, nothing's comparable, but similar to the high titanium basalts of Apollo 11. It also returned feldspathic breccias of a great diversity, but clearly one of the highlights was the discovery that Jack Schmitt made of the orange pyroclastic glass. This, if we didn't have that sample, we would still be arguing what these materials, these small components in our lunar soils were. That was a major breakthrough in understanding some of the unusual volcanic characteristics of the moon. And of course, we couldn't do without Luna 24 from the Russians. This was the first time we had samples of the various very low titanium basalts, which we had a tiny fragment in one of the deep drill cores, but it showed that there's even greater diversity in the basaltic terrain that we had sampled throughout the Apollo program. And this was the last sample return from the moon, and it opened up a whole new understanding of basaltic volcanism on the moon. So this is not to say that we're done. There are a large areas of things that we still have not yet done, and the samples and the cyclical analyses that have happened over the last 50 years have highlighted there's a large number of areas that we want to pursue in the next 50 years. And of course, the volatiles at the pole is one of the prime. So let's touch on these briefly. You know the near side of the moon, the far side of the moon, which Jack was just talking about, North Pole, South Pole. These are albedo images that are probably familiar to you, but these albedo images were taken with the LRO laser altimeters, so they're albedo without any shadows. Okay. Okay, so you can take that data and then look at the North Pole and the South Pole directly on and see the albedo of the moon if you were looking directly down at the poles. And what this tells you is that, and here's a couple of locations if you can't quite figure out where you are from the North Pole and South Pole. But what this tells you, if you look at the bright material, that's the feldspathic terrain, both the North Pole and the South Pole of the moon are in feldspathic highland terrain. And they're more than 100 kilometers from any of the more mafic-rich, more basaltic or deep-seated material. And this is important because, as you know, one of the reasons we want to go to the poles is because they're of great interest for the volatiles, these shadowed areas that we expect have sequestered abundant volatiles. Great interest. Many of the missions that are planned and are on the way to the moon are targeting the South Pole of the moon, and the South Pole has been the principal area of activity. I'd like to diverge a little and make a suggestion here. This alludes to the contamination issues, that with all these activities that are now progressing towards the South Pole, which are very important because of the volatiles, we don't understand those volatiles yet. They could have billions of years of history of the solar system. It would be prudent for us to assure that we concentrate those efforts on the South Pole and keep the North Pole pristine until we understand what these materials are. So be thinking about that. Okay, other diversity areas, the sequestered volatiles at the South Pole, the mafic materials in the South Pole Aiken. This is a huge topic. We could have an hour or two discussion on it. We also understand there are very young volcanism, much younger than any of the samples that we've obtained, and we haven't explored those yet. There are unsampled types that we found in the remote sensing that we do not have in the samples. The magnesium spinel component is one of the key elements. There's a variety of areas that contain that. There's a vast feldspathic highland terrain on the far side that we would really love to have samples for in order to expand our understanding. These are just examples, and I'm sure each of you could identify 10 more. Okay, and this is the next to last slide. Okay, I hope I've given you a taste of the cyclical nature of exploration of the moon. The various components were not done yet by any means, and the importance of both the diversity of sites, the diversity of samples, and the ground truth is essential as we move forward in the next 50 years. Thank you.
Okay, who has questions for Carle? Dana.
Hi, Dana Hurley from APL. So Carle, for volatiles, I mean, is that something that you think we're better off doing sample return or in situ analysis?
Yes. Clearly, we will probably do in situ first. But in order to get this large understanding, we definitely are going to need to be doing sample return. And there's aspects about the sample return which the community ought to be really thinking seriously about. It's on par, perhaps even more important than a comet sample return, because it has billions of years of history in it, as you probably know.
Okay, one more up here.
Samson Fan from SRI International. I was hoping you might be able to expand a little bit more on your thoughts on the robotic uses on the moon, especially from your perception as a geologist.
How much time do we have? I don't think there's any robotic experiment that is not valuable. Every time there's been a mission to the moon, we've learned an enormous amount, even with small missions, even with very complex missions. I can't answer that with a 2-minute window, but it's a good question.
Okay, one more quick one right here.
Carle, in talking about the moon as the 8th continent, you're ignoring that's all right for geologists, but the top 2 to 5 centimetres is more extraterrestrial. The top 2 to 5 centimetres of dust is more extraterrestrial in its chemistry, being bathed by the solar wind, its nanoparticles and so on.
Thank you for that comment, because that's something I didn't explicitly discuss in this brief discussion, namely the regolith includes both, well, actually, let me divert a bit. It includes some of the most recent history because it's been exposed to all these elements of the solar system and retains that record and is extremely valuable both for the uppermost, which retains the current environment, as well as deeper ones, which are more difficult to access but are important in understanding the history of our place in the solar system.
Okay,
Okay.
good. Thank you.